this video on integral relations on control volumes, we're gonna discuss conservation of mass. So if we look at the fluid volume, then remember a fluid volume was we selected a given amount of fluid and then just follow it in time and keeping all the molecules. And that means that the change of mass on this fluid volume must be zero, because the mass cannot appear nor disappear. And therefore, we're going to use now Reynolds transport theorem. We're going to take as our extensive property the mass, and as our intensive property specific mass, or mass divided by mass, so simply 1. And what that's going to tell us is that the change in mass in a fluid volume, which is 0, is going to be equal to the change over time of the integral over the control volume of rho dV, and then plus the integral over the control surface of rho v minus vc dot n, and dx. And this is the more general statement about the mass conservation law. This is true in all situations. Of course, we also saw the simplified version of the Reynolds transport theorem, so we can write again dmf dt, which is 0, as the change of mass in the control volume minus the sum of the mass flowing in the inlets, and then plus the sum of the mass flowing out in the outlets. And in many cases, this is going to be enough, and that actually you can think of it as well as being always true, but just remembering that this sort of part here, in some cases, we will be able to compute it in an easier manner. In the more general term, it's going to be this integral, and the same here. This change of mass is related to the change of this integral. Good. And of course, that's general, and with that we can solve all the problems, but let's look at some cases where we can simplify things. So we look at these simplifications, and again, let's consider simple case. We don't know what's going on the other side, but we're having this end of the tube. We're having our control volume in here. That's marked in blue. And then we're going to look at the outlet. We're going to have this certain velocity at the outlet. And so let's do some assumptions. Let's assume that V is constant. And by constant, I don't mean constant in all the control volume, but only constant in the outlet, in the surface of the outlet. Let's also assume that rho is constant, and also in the same place. And then what we will have here is the mass flow at the outlet, which in principle is simply the integral over the outlet, surface of the outlet of rho, change in velocity, dot n times ds. Let us also assume that bc is equal to 0. If not, we will just work with v minus vc. In this case, since everything is constant, we'll have that this is equal to rho and the velocity at the outlet, and then the integral over the outlet surface of ds. And of course, this is simply the area at the outlet. So this will be rho v out and s out. And of course, we can do the same if we look at the inlet, and we'll find exactly the same, rho v in and then s in. And if you want, we can write that the density might also vary between the inlet and the outlet. And of course, always remember, this expression here is only true when these conditions are fulfilled. Otherwise, we'll have to go to the more general integral equation. So that's one big simplification we can do. Another one, say we have a tank, something like this, and our control volume now is this fluid inside the tank. And again, if rho is constant, then what we will have is that the mass on the control volume, which by definition was the integral of rho dV, again, if rho is constant, it can go out, so we will just have rho times the volume itself. And the same, this is total mass. We can do the same with the mass flow. If rho is constant, it can be written as rho times the volumetric flow. But again, only if rho is constant. So if we put all together, all the simplification together, we will find this simplified version of mass balance, which is a change of the control volume minus the velocity in times S in and plus the velocity out plus S at times S out. And of course, this is going to be useful, but remember, this is only true in these cases where everything is constant. And finally, let me make this caveat that if we do have a velocity vector in this direction, that's not the one here. This would really only be the one perpendicular. Because of course, the mass flow, only the, or the volumetric flow, only the perpendicular component of velocity is the one that, that is important. So this would be Vn. Good. So finally, before finishing, let us consider the mass balance equation between two states. So if we write it in the simplified version, but this would apply also in the more general case, we will have that D, the change of mass, minus the mass flow in, plus the mass flow out, is equal to 0. And that's written in the form of a differential equation. But say that we want to, instead of having it in continuous, we have an initial state, and we're moving towards a final state. And we have a certain delta t, say 1 second, 1 hour, 1 year, whatever. In this case, what we can do is integrate this whole equation as a function of time. We do that. The first one is just the integral of the derivative in time. So this will simply be the change in mass between the initial and final state. And then remember that this is flow per unit time. And therefore, if we integrate it over the time, this is simply going to be M in, which is now, notice that what's basically changing is that the dot is not present anymore. And this is the total flow between the initial and final states. And of course, the same with the mass out. And this again is 0. So notice that basically we're written exactly the same, but conceptually it's a bit different. This is a derivative, this is the change, this is the mass flow per unit time. So this is the derivative, this is the change, this is the mass flow per unit time, and this is the total mass flow between two states. And that's enough for the mass balance study.